So what we have now is subsequences, each of which is good at a finite number of points, but what we really need is a subsequence which is good at infinitely many number of points. Okay, and for this one cannot just go further and further in this choosing of subsequences because nothing might remain. And so maybe let us look a bit more what we have done here. So here I have drawn essentially the elements in my sequence. So here in the first one, that's my original sequence F. So that's F0. So I mean this is the first, the second, the third, and so on element in this sequence. Okay, and then in the first step, we construct a subsequence of this, which I call F1, where I'm just choosing some of the elements here, but the good reason for doing this is that this subsequence converges at the point x1. Okay, and then in the second step, I'm choosing a subsequence of this sequence, which then improves that it also converges at x2. And of course, it's not losing the property that it's converging at x1. So I have here a subsequence f2. Okay, in the third step, I'm improving further so that I have now get something which converges at x1, x2, and x3. And this here is a subsequence of this sequence. And of course, all of them are subsequences of the original sequences. So if I go up to level k here, I have a sequence which converges at the arguments at x1 up to xk. Yeah, but now I want a subsequence which converges at not only at finitely many, but at all the rational x's which I have. And of course, I mean, the first idea, maybe I just continue here, choosing subsequences of subsequences and so on, and I just take what is left over in the limit, but I mean, there might be nothing left. So that's not a good way. So I really have to choose subsequence in a better way, which essentially has all the good properties of all the subsequences which I have here, but which still is a sequence. There remains something. And that's the famous diagonal element, that actually we are taking one element from each of those subsequences so that actually what we have behaves in a limit behavior as each of the subsequences, but I really have elements. And so what I'm doing is I'm just taking the first element from the first sequence, I'm taking the second element from the second sequence, and I'm taking the third element from the third sequence, and so on. The fourth element from the fourth sequence, and so on. So what I'm taking is actually a diagonal kind of sequence, and that's what I will call G. That's my sequence G. So officially, so Gn is a sequence, and the nth element is just the nth element from the nth subsequence which I have chosen here. And now, so this G is actually it's a subsequence of all of those guys. Maybe not from the beginning on, but at least later on. So I mean, G, of course, is a subsequence of this guy here. Then G is, I mean, this guy here is not, because of this guy, it's not a subsequence of this, but if I forget the first element, then it's a subsequence of the second one. Then G is also a subsequence of the third, and so on, if I'm erasing finitely many of the first elements. But for the limit behavior, I mean, only if n going to infinity is important. So I mean, the first finite number of first elements don't play any role for the limit behavior. So this means this G, this Gn, so this is really a subsequence of the original sequence. And actually, it's also a subsequence for each of the chosen subsequences, at least eventually, which means from some point on. Because, I mean, of course, beginning elements, first elements there might not be there. So, I mean, so this element of G1 is not part of those sequences. So, but if I forget about this, then the rest of my sequence G is a subsequence of this here, and so on. So this means Gn is, for each k, eventually, so this means with the exception of maybe finitely many points, a subsequence of the sequence fk, which was chosen in the case step. Okay, and this means the limit behavior at the point xk of my sequence gn is the same as the limit behavior of the sequence fk. But fk was chosen in such a way that the limit behavior is correct for the point xk. So this means the gn, because it's a subsequence of fk, has the same limit at the argument xk. So this means that, and this is true for all k. So for each fixed k, we have that the limit n going to infinity of my sequence gn at the point xk is the same as the limit of my sequence fk at this point xk, if n goes to infinity. Yeah, and the sequence fk was constructed in such a way, or chosen in such a way, that the limit exists, and this was the point yk. Good. Okay, and so now, yeah, with this great diagonal trick, we really have now produced a subsequence of the original sequence, which at least at all rational points converges. Okay, and this, of course, now is now, at least we have now, yeah, something from which we can work. Of course, we still have to prove quite a bit, namely we also need the convergence at the irrational points, and what we are looking here at is only pointwise convergence. So we also need uniform convergence, but at least we have now a good limit object already there, and hopefully equicontinuity is strong enough to give us all the other things. Up to now I have not used equicontinuity. Good, okay, so this Gn is our candidate, and so maybe let me write down what we know and what we still have to show. So first we know that, of course, the Gn is a subsequence of the original sequence Fn. Okay, and it has some good convergence behavior, but only, for the moment, only at rational points. So the Gn of x, of x converges, but for the moment we know this only for all rational x in the interval 0 to 1. So for x in 0, 1, but only the rational ones, so the xi's. Okay, and so I mean we still have to do quite a bit. So we still have to show that this g is actually our uniform limit of this, this Gn is okay, converges uniformly, so it's a uniformly convergent subsequence of our original sequence. So for this, we have to see that first of all, of course, pointwise, it should converge for all x, not only for the rational ones. So Gn of x converges for all x in the domain 0 to 1, and then of course the convergence should not only be pointwise, but it should be uniform. Okay, and of course this is much more, and in general does not follow from what we have done here. I mean, up to now I have not used equicontinuity. So the argument up to here I could do actually for any bounded sequence of continuous functions. But now that I can improve this to what I really want, for this notion of equicontinuity will be the crucial one.